All right. Hello, everyone. Let's get started. So, in the last 10 weeks of the course, we have looked at the electronic devices. We have understood how to analyze their properties in sufficient depth, I believe. So now, in the last 2 weeks of this course, we would like to focus on optoelectronic devices. Why are we interested in them? Well, it turns out that the optoelectronic or the photonic devices are very, very important part of the current technology. We see, solar cells, LEDs, lasers. All of these are optoelectronic devices, and we can apply the concepts that we have learned so far to understand how these devices work. So, because of this critical importance of this technology, we would like to discuss it now. And to start with, we'll have to understand optical absorption. So we have briefly mentioned it, multiple times in this course already. So let us say you have a semiconductor, and then we shine light on it. What happens? We said that, let's say the semiconductor has a band gap of, in this case, let's say Eg. Okay. If the energy of the photon is less than Eg, the photon does not have sufficient amount of energy to excite an electron hole pair. We talked about it already. So now, if the photon has energy equal to Eg or greater than Eg, what would happen? Well, it will take an electron out of the conduction band and put it into the valence band. What does it mean physically? Well, when the electron is in the valence band, we are saying that the electron is bonded to the silicon atoms. It's part of a covalent bond. Now, when a photon hits the material, the covalent bond is broken. The photon has sufficient energy. When the photon has sufficient energy, the covalent bond is broken, and then the electron moves into the conduction band, meaning that it can freely move about in the lattice. So, essentially, electron hole pair is produced. What happens to the photon? Right. The first effect is you have electron hole pair production. And what happened to the photon? Well, photon is annihilated. Photon is destroyed or annihilated. Right. There is no more a photon. The energy of the photon, right? Photon is essentially energy packet. So the energy is consumed by during the process of breaking the bond, and there is no more a photon, right? So the photon is destroyed. So how do we quantify this? So let's say if I take a piece of semiconductor and I shine, let's say 100 photons on that. Okay, 100 photons is a very, very small number, but let's say I managed to shine 100 photons on this semiconductor, and let's say the thickness of the semiconductor is L or T, whatever. Yeah, L. Okay. If the thickness is L, and we know the band gap, of course, right? Eg, something is there, right? So how many photons will come out of this? Right? That's a problem we want to understand. So to analyze this, well, the number of photons that comes out is the photons that are remaining, right? Some of them are getting absorbed, and the absorption will lead to reduction in the number of photons, correct? So let's say I have 100 photons incident on the left side now. Let's call it maybe x equal to 0 here. X equal to 0, there will be 100 photons. But the moment, let's say they go, let's say L by 2 distance, right? Midway through, there might be only 50 photons, right? 50 of them they got absorbed. So basically what we are interested in is, let's say if your initial number is n or n naught, let's say, okay, if the initial number of photons is n naught, how much, initial number of photons, how many photons are surviving at a distance x, right? So what we are interested in is dn by dx, the change in the number of photons as a function of distance. Well, obviously the change is going to be proportional to the number of photons at a particular distance, right? So this will be proportional to n. So therefore, what we do is we say that dn, and well, the number of photons reduces, so there should be a minus n here, okay? It should be proportional to minus of n. So as the number of photons is larger, the greater number of photons will be reduced, right? So dn by dx we will introduce a constant of proportionality and say that we call it alpha. So dn by dx is equal to alpha times n. Okay. So if you solve this, it turns out that this will be n equal to n naught exponential minus alpha x. Sometimes we can also, instead of talking in terms of number of photons, we can also talk in terms of intensities. Okay. The optical intensity that gets transmitted is essentially equal to I naught exponential minus alpha x. The same thing. Okay. So this is, I can call it transmitted intensity. Okay. Now we can plot this, and that is what is shown here for two different values of alpha. And this alpha, we'll call it as absorption coefficient. This I'll call it as absorption coefficient, and its units, generally we will refer to them in terms of centimeter inverse, per centimeter inverse. Okay. Per centimeter rather. Okay. So if you have a large absorption coefficient, that means the number of photons will decay faster, the intensity will fall faster. That's what is shown here, larger alpha. And if you have a smaller alpha, the absorption coefficient is small, then the photons will continue to go forward. So now, based on our knowledge of semiconductor devices, is alpha fixed quantity or a material, or what are the parameters that affect alpha? So think about it. So what parameters influence alpha? Well, we know that if the wavelength, it's definitely wavelength dependent quantity, right? Because we know that wavelength, if it is larger than, if the wavelength is smaller than Eg, that is energy is larger than Eg, then it will be absorbed. If the wavelength is longer, right? So you know that energy is inversely proportional to lambda. So if the wavelength is longer, the energy of the photon is smaller than Eg, let's say, and then it will be transmitted. So alpha is going to be dependent on lambda. Okay, that is one critical parameter. Okay. So, well, I mean, in the sense it depends on the band gap. Indirectly, that we can say that it's dependent on lambda. Okay. So, of course, there's also other things like there's some variations in terms of temperatures and other parameters, and even the smoothness of your surface. So, but we will not get into it. Those are like secondary effects. So, this is how you will calculate optical absorption. So, why is this important to us? Well, it is important because it helps us understand many things that we see around us. Like for example, I'm wearing glasses now. So, why are these glasses transparent? You might ask, right? So, the reason they are transparent is we know that the band gap of silicon dioxide, glass is essentially silicon dioxide, and band gap of silicon dioxide is Eg is about 9 eV, right? And one of the easy ways to calculate, the photon energy is basically, let's say I have a photon of, let's say, 500 nanometers. Okay, 500 nanometers means it is equal to 0.5 microns. So what is the energy of that photon? That energy of photon will be given by if lambda equal to 0.5 microns, right? Energy will be 1.24 divided by 0.5. Now we have to write lambda in microns, and this will be 2.48 eV, right? So if I have a visible, like this is green light, lambda equal to 500 nanometers is essentially green light. Okay, so when you shine green light on a piece of glass, its energy, the photon energy is smaller than the band gap, so it gets transmitted. Okay, so you can actually analyze and understand that the visible range of radiation is from 300 to 700 nanometers. Okay, so if you shine any of these photons on a piece of glass, they get transmitted. That is why glass is transparent. Okay. The same analysis can be used to understand why silicon is not transparent. This is an image of silicon I have taken from the web, and we know that silicon's band gap is 1.12 eV. What happens if I shine a visible light photon on it? right? Visible light. Let's take the center one, 500 nanometers. So it is 2.48 eV energy of the photon. And if you shine 2.48 eV photon on a silicon piece, then it definitely will get absorbed. And that is why if you put a piece of silicon between you and a light source, light will not pass through it. And that is why we see that it is not transparent. Okay. And we also have some interesting materials like gallium arsenide, gallium phosphide. Here I've taken another image. This is a wafer of gallium phosphide, and gallium phosphide I think has a band gap of about 2 eV. About I don't remember the exact number, but EG should be about 2 eV. Okay. So what that means is the red photons are transmitted. Okay. So if you this is okay, let's look at this figure, then that will help you understand this. So on the x-axis of this figure, we are having wavelength, okay, 0.2 to 1.8 microns, okay. On the top, for the same corresponding wavelengths, we have the energy calculated. So simply we can calculate it by 1.24 by lambda. So we have these energies given, okay. So if the energy is 2 eV, so in this scale, if the lambda, if the energy of the photon is anywhere here, it will get transmitted. Only for the photons which have energy greater than this will get absorbed in the gallium phosphide. Okay, so that's what is happening. So the red photons, because generally 700 nanometers, 600 nanometers are red region of the spectrum. If you go to violet, it will be blue region of the spectrum, we say. So the red region of the spectrum is getting transmitted. That is why it looks reddish yellow. This is gallium phosphide. So you clearly can understand that the band gap influences the transmission properties of a material. And this picture here on the right is showing you the absorption coefficient for various semiconductors. Okay. So you notice some trends here, which is all the materials have low absorption at long wavelengths. Okay. All of these materials shown here. Okay. And let's get the familiar ones to us, which is silicon. Silicon is shown in blue here. So absorption is increasing. And this is a logarithmic scale, remember. Okay. So if you go to lower wavelengths than the band gap, so band gap I'm using in terms of wavelength or energy, I can use equivalently. So if your wavelength is lower than the band gap, then it's getting absorbed. Okay. Equivalently, if the photon energy is greater than the band gap, it's getting absorbed. Okay. Similarly, you can look at gallium arsenide. Gallium arsenide has a very steep increase in the absorption and then continues to increase further to lower wavelengths. So what is the difference? Why gallium arsenide has a steep absorption? Right? Why gallium arsenide has steep absorption? Right? And with wavelength just below band gap, it simply absorbs very fast. Why? If you notice, a few other compounds like indium phosphide also has a very steep absorption. I'll talk about these other things in the next few lectures. We will get back. But if you look at germanium, germanium has a more gradual change in the band gap. Of course, germanium's band gap is only 0.8 eV, roughly around 0.8 eV. So that's why it starts absorbing even at longer wavelengths, right? So this is how the trend is. So the reason this happens is something to do with the direct and indirect nature of a band gap. I mentioned this in the beginning of the course, wherein we talked about the EK diagrams and how to analyze how we get EK diagrams, and we mentioned that if the peak of the valence band is coinciding with the bottom of the conduction band, we call it a direct band gap semiconductor, and that's what we have here, gallium arsenide, which is a direct band gap semiconductor. Whereas if you look at silicon, if you look at the EK diagram, it turns out that the peak in the valence band is not coinciding with the bottom of the conduction band. There's a difference in K, because of which silicon, this is called as an indirect band gap semiconductor. And generally, indirect band gap semiconductors are not efficient absorbers of light. Okay? Because you essentially need an additional phonon to get, because this K is there. There's a difference in K, right? This is, I would say, delta K, you can call it, the difference in energy. And we already saw that the photon has very, it has good amount of energy, but it has negligible momentum. So a photon can only make a transition happen from here to here. It cannot make a transition happen from here to here. So for this, you need a phonon, which will assist the transition, and it is a second order process. And because of which, the optical absorption in indirect bandgap semiconductors, in indirect bandgap semiconductors is not efficient. It doesn't mean that they're useless. Okay? They're still useful, but the absorption efficiency is less. Whereas in a direct bandgap semiconductor, it's very, very efficient. There is no momentum requirement. Only energy conservation is required. And because of which they're very, very efficient in absorbing the photons. So that's why you look at it, there is a very steep increase in the absorption above bandgap in a direct bandgap semiconductor material. Whereas in indirect bandgap, you have more, more. If you have higher and higher energy, you need more phonon, more phonons to help the absorption process, and eventually it increases, but it's not. It's a gradual process, gradual increase. Okay, this is one key difference between direct and indirect bandgap semiconductors. Okay, let's try to. This is mainly what I wanted to talk about optical absorption. Let's try to solve a couple of problems so that you get confident about it. Okay. So this is an example from the textbook. So you are given, calculate the thickness of a semiconductor that will absorb 90% of the incident photon energy. Whether you talk of incident photon energy or incident intensity or number of photons, all of them are equivalent. Okay. So when will it absorb 90% of the photon energy? Well, we know that law is basically I equal to I naught exponential minus alpha x, right? So if let's say initial photon energy is 1, so it has to lose 90% of the energy, right? What is the thickness? We want to find this thickness, right? What is this thickness? So let's say the remaining energy is basically going to be 0.1, right? So 0.1 equal to exponential minus alpha x. So I need to use some alpha. So, okay, this number is given, I just copy pasted. Let's say it is 10 power 2 per centimeter inverse at 500 nanometers, just as an example. If you do that, quickly you can calculate this. So the length, right, or x in this case, right, is going to be ln of 0.1 divided by alpha in centimeters, right? So alpha is rather 10 power 2 here, right? This is going to be centimeters, x in centimeters. So this is going to be ln of 0.1, I think is minus 2.3. So this will be equal to 2.3, minus will cancel out, 2.3 divided by 10 square. So that is going to be 0.023 centimeters. This is the thickness. So in other words, this is 0.023 centimeters. Okay, 0.2 millimeters. Okay, so what happens if the absorption coefficient is larger? If in case alpha is like 10 power 4, this is a case 2 basically, alpha equal to 10 power 4 per centimeter, then x is going to be minus 2.3 divided by 10 power 4. So that is going to be 2.3 into 10 power minus 4 centimeters. So that is equal to 2.3 micrometers. Okay. So this is going to be the distance. So we just need, if absorption coefficient is strong, you just need 2.3 micrometers of thickness to absorb 90% of the energy. Okay. So you saw these pictures here. For example, these wafers are not transmitting. Silicon wafer is not transmitting, whereas glass is transmitting. But of course, we assume that all of them have similar thicknesses, which is in this case a few millimeters. Silicon might be 500 micrometers. This might be a couple of millimeters. Wafer in gallium phosphide, and typically glass also has 500 to 750 microns. So they are reasonably thick material, and that's why you see that either there's complete absorption or just transmission. If you make glass which is let's say meters of thick, then probably you will start seeing some absorption. Okay? Just because the thickness is large. Absorption alpha is less for glass, but the thickness is large. If the thickness is large, there can be some absorption. All right. So this is how you can calculate the different absorption coefficients for when light is incident on a semiconductor. Now let's do one more problem, and this is about generation of electron hole pairs. So we said that when the photon is absorbed, it gives rise to electron hole pairs, right? So what is the rate at which you can generate these electron hole pairs? So calculate the generation rate of electron hole pairs given some incident intensity. So this is, we are asked to calculate for gallium arsenide at room temperature, and photon intensity incident at a particular point is 0.05 watt per centimeter square. Lambda is this at this wavelength. So the intensity is typical of sunlight. Okay, yeah, well, this intensity is, yeah, typical of sunlight. So how many electron hole pairs are produced? Well, to calculate that, we need to realize that what is intensity? Intensity is essentially the number of photons per centimeter square, or per centimeter square, times the energy of the photon, right? So the intensity of the photon is simply number of photons. I'll just put it as hash. Number of photons per centimeter square per second, right? Into E of h nu, I'll say, okay? Or h nu of the photon, energy of the photon, right? Energy of the photon. This is going to give you energy per second will give you power per centimeter square will give you energy, power and intensity, correct? Yeah. So so what is this number of photon? I can call it maybe n lambda. That's even better. Okay. So we are given. We need to calculate what is the energy of the photon. How much is the energy of the photon? Of lambda equal to 0.75 micrometers. So energy of this photon E lambda is going to be 1.24 divided by 0.75 microns. Okay, in this expression I have to always put the denominator in micrometers, not in nanometers or millimeter, only in micrometers. Then it works. Because this comes from hc by lambda, you can calculate and see that it will turn out to be this. Okay, this is going to be EV. So this will be 1.24 divided by 0.75 is going to be 3 by 4, right? 3 into 4. 3. So this will be 0.41 something. So this will be something like approximately 1.64 EV, something like that. Okay. Let's say this is 1.64 EV. This is energy. So how many photons? Well, to calculate that, we have to go back and substitute here. Number of photons in n lambda is going to be intensity, which is 0.05 watts per centimeter square. I just will write it deliberately. Okay. Divided by energy of the photon is 1.64 EV. Okay. And by the way, this is EV, so this has to be always multiplied by 1.6 into 10 power minus 19 to get joules. Okay. So this will give you the number of photons. So if you calculate this, you will calculate it. I guess it will turn out to be some number, in 10 power 15 to 10 power 17, some number it will be, okay? Because this is 10 power minus 19, it will go up. So 10 power 19, and then, okay, let's approximate it, 10 power 19. So this will be 5 into 10 power 19, 5 into 10 power 17 divided by 1.6 into 1.6. 2.56, right? 2.56. That's roughly going to be 2 into 10 power 17 photons per centimeter square per second. Right? This is the rate at which the photons are incident. Okay. Now, but you're not asked number of photons. You're asked how many electron hole pairs are generated, right? So how do you calculate the number of electron hole pairs? Well, to calculate that, we have to look at the absorbed, number of absorbed photons, right? So this will be number of absorbed photons is going to be alpha times the incident, number, right? The, at particular point, the absorption coefficient will give you how many photons are getting absorbed, right? So the alpha is basically per centimeter inverse, okay, into 1 over centimeter. This is the units into n lambda you do, okay, and this is what gallium arsenide and 0.75 microns. Let me just go back. Gallium arsenide, 0.75 microns, so 0.75 somewhere here, right? Just generally, yeah, gallium arsenide band gap is 870 nanometers. So 750 is just above band gap. So there's a very steep increase, okay? So we can take the absorption coefficient of this guy, gallium arsenide. Let's take it to be 10,000 centimeter inverse. That's a typical number because it's above band gap. We can roughly take that into 2 into 10 power 70. Okay. So if you calculate this, what are you going to get? Well, 10 power 21, right? 2 into 10 power 21 EHPs per centimeter cube per second. So this is the rate at which you are generating the electron hole pairs. Okay. So yeah, this is a rate. Yes. Okay. Of course, this is just the generation rate is going to also depend on the tau, the minority carrier lifetime. So this is just the number of photons absorbed, right? But then there's also going to be influence of the steady state concentration of photons is going to be dependent on the tau, because we saw that when we analyze the non-equilibrium statistics of semiconductors, we saw that once you have this electron hole pairs produced, some of them are going to get recombined, right? So there will be an equilibrium concentration in steady state. That's going to be this number times tau. Tau is typically 10 power minus 6 or something. So I would say in steady state, there will be about 10 power 15 electron hole pairs in the semiconductor. All right. So you can analyze these things. All right. So this is basically about optical absorption. So given an absorption coefficient for a particular material at a particular wavelength, you can estimate how many photons are absorbed and how many electron hole pairs are generated. By the way, when we calculate the number of electron hole pairs generated, we assume that all the photons are getting converted to electron hole pairs. That doesn't happen. There's a certain efficiency. Sometimes you're given the efficiency, so you have to just scale it by that number. Let's say the efficiency is 90%. Then you scale it by 90% and get the final number. Okay. Right now in this calculation, I assume that all of the photons are getting absorbed. Okay. And they're resulting in electron hole pairs. That's a iffy condition. Okay. That doesn't happen in real life. All right. So this is about optical absorption. So I'll stop this video here. So once we understand this, now in the next video, I'll talk about solar cells, which is a very, very important semiconductor device nowadays. All right. I'll see you there. Thank you so much for your attention. Have a great day.